Everybody in? Okay, so welcome to the fourth lecture in this series. This is a more or less a tribute to one of my fabulous former students, José Desharnais, who made the crucial contribution to the proof that I'm going to describe. She's a French-Canadian woman and not that fluent in English. So when she presented this result at LIX several years ago, Von Pratt asked her a long and convoluted question at the end that's hard to understand and harder to answer. So she just looked at him and said, "I'm sorry, I've used up all my English words." So what I'd like to talk about today is the logical characterization of this bisimulation. So this is a principle for reasoning about the behavior of probabilistic systems. And bisimulation is an equivalence relation. You can think of it as being defined on processes, but perhaps it's simpler to think of it as being defined on the states of a transition system that behave exactly the same in some observable sense. So I have to make these definitions all precise. And what was striking was the fact that there is a nice modal logic which gives you a complete characterization of this relation in the sense that two states are exactly behaviorally equivalent if they agree on all the formulas of this modal logic. Okay, so theorems like this have been known. Van Bentham and then Hennessy-Milner proved such a theorem for label transition systems. These are well-known results from the 70s. But the probabilistic analogs of this emerged in the 80s. And then this result is for probabilistic transition systems, but defined on continuous state spaces of a certain kind, where it was perhaps unexpected that still something as discrete as a simple modal logic could still characterize behavioral equivalence. So I'll give a brief summary of label transition systems, and then I'll move on to labeled Markov processes by the simple device of replacing the transition relation with probabilistic relations that I introduced yesterday. And then I will give some intuitions and examples. But then I will have to make a digression into the theory of Polish and analytic spaces. And then I'll get back to the proof. And then I'll say a bit about simulation, which is, of course, not the same as bisimulation, but closely related, and for which there is also a logical characterization, but with an unexpected twist. And finally, I'll say something at the end. Miraculously called concluding remarks. So the transition system, you have a set of states, a set of labels or actions, and a transition relation, typically written with this arrow. And these transitions could be indeterminate. And again, the indeterminacy is not quantified in any way. So these are the standard labeled transition systems. I didn't know this at the time, but they were introduced by my former master's thesis supervisor, Robert Keller. Anyway, so these are labeled transition systems and are models of many kinds of simple, discrete, dynamical systems. We will typically write the transition label on top of the arrow, rather than like that as a triple. Okay, so just simple examples. We might have a four-state system. You see the state S under an A transition could go to one of two places. It's not determined to which place it goes. Once it gets to S2, it can do a B transition and get to S3. In S1, it's already dead. And here's another example. You see it could go to two different states under different transitions. It so happens that the transitions out of S0 are determinate in this case. They need not be. And for example, when you get to S1, you see the indeterminacy in the C-labeled transition. Okay, so these are typical examples of labeled transition systems, and one typically has some story about vending machines to explain these things to students. Okay, so bisimulation. So I just want to say this quickly because these are well-known things in this case. So we will say two states are bisimilar if the transitions from one state can always be matched by corresponding transitions of the other. So if S can do an A transition to S prime, there's some state T prime such that T can match that, and the resulting pair are themselves bisimilar, and vice versa. Okay, so I won't always write both counterparts. I might often say just and vice versa to indicate the symmetry of the relationship. All right, so this may appear slightly circular, but it isn't, and it can be made rigorous in various ways. So here's one. So we'll define a bisimulation relation. So please take note of the fact that I've now used the indefinite article. A bisimulation relation to be an equivalence relation on the states such that if they're related by that relation, and then one of them does an A transition to a state S prime, then T can also do an A transition to a corresponding state with the S prime and the T prime related, and again, vice versa. Now, there's nothing circular about this. You've given me a relation, and you can check whether or not it has this property. It might not. If it does, then indeed, we will call it a bisimulation relation. So it is just a condition on R, and now we will say S and T are bisimilar if there is some bisimulation relation R with that property. So you can say bisimulation is the largest possible bisimulation relation that one can find. And indeed, there is a nice greatest fixed point characterization of it that you get by iterating an appropriate functional on the lattice of relations. Okay, so this is the version that is used most often, and the one that I will use in the probabilistic setting, or at least the one I will base the probabilistic version on. So labeled Markov processes are the probabilistic analogs of these labeled transition systems. So again, you have a set of labels and transitions, but now the final state is actually governed by a probability distribution. It's not just purely indeterminate, so it's quantified. And I emphasize that there is no other indeterminacy. So you will see a number of different models. People talk about mixing probability and non-determinism, perhaps saying once you execute a certain action, then one of a set of probability distributions is chosen, and then further the final state is determined by that distribution. So I'm not doing that. Everything, all the indeterminacy is quantified in this traditional probabilistic fashion. Okay, so there is all the probabilistic data is internal. Okay, so once an action is chosen, then there is some probability distribution governing the final states. We are not attempting to say how those actions are chosen. We're not saying A happens with probability half or anything like that. We're just saying given an action, here's how it responds to that action. And what is important is that we don't actually observe the state of the transition system at all. You don't get to see what state you're in. You just get to see what actions you can perform. So you can think of this as being modeled by some kind of black box with some buttons that you get to press. These buttons are the actions, and perhaps the system will actually reject a certain action. So you press the button and you will hear perhaps a satisfying click, and you know some transition has happened, but you don't get to see where it's gone. All you get to see is that yes, this action was accepted, and if you do it enough, you will get to perhaps associate a transition probability with that action. Okay, right. And I should mention, it's not on the slides, but I always have sub-probability distributions, because I always allow you to perhaps have actions that are just not accepted by the machine. As for example, in our standard vending machine examples, if you press the button to serve you coffee before you put in the money, it just won't respond. Okay, so so sub-probabilities govern the actions. So these kinds of things were studied by several people. Larson and Sko are prominent names in this area. But the new thing that I and my co-authors did was to start studying this on continuous state spaces. Okay, so right now I'm just using the somewhat vague term continuum. I will give a more precise definition presently. Okay, so how do we define transitions on top of these continuous state spaces? Well, this is what I talked about yesterday. We use Markov kernels, and I try to argue from the categorical viewpoint that these are the correct generalizations of the notion of transition matrix or binary relation. So Markov kernel, just to remind you, is a two-argument function. It takes a state and a set. If you fix the state and let the set vary, you get a sub-probability measure. If you fix the set and let the state vary, you get a measurable function. And so though apparently asymmetric, these are indeed the probabilistic analogs of binary relations, and they share much, but not all, of the algebra of binary relations. And also they generalize the notion of matrix, and the composition law generalizes the notion of matrix multiplication. So one is used to using transition matrices for Markov chains and multiplying them to describe successive transitions. So it's the exact same thing happening here in the same way. So let me give a formal definition of these things, which I call labeled Markov processes. So we have a set. Because it's in general a complicated space, one has to pick out a sigma algebra of measurable sets. There's a set of labels, and for every possible label, there is a transition probability function tau, which is satisfies the following conditions. So first of all, the set together with its underlying sigma algebra is the Borel algebra of an analytic space. And suddenly this thing has popped out of nowhere. So yes, I was as surprised as you are when this entered the subject. So let me punt on that for the moment. But presently, you will see why I had to do that. So analytic spaces indeed are a restriction. It's not all measurable spaces, but they are extremely common. Most of the things that you see in science and engineering are indeed Polish spaces, let alone analytic. And if you wake up one morning and you find you're not in an analytic space, I would be worried. Okay, so this is the transition function, which is a Markov kernel, and it has the type that I've been talking about before. As I said before, it's a probability measure in one argument and a measurable function in the other. Now, probabilistic bisimulation closely mimics what I did for ordinary bisimulation. So this definition, sometimes people think theorems are hard, but definitions are even harder sometimes. This took us a long time to come up with, and it was shocking at the end that it was so similar to the original definition of bisimulation, because we went through a long detour with lots of category theory. But I promise to spare you category theory today. So this is the definition we finally converged on. So sometimes we introduce an initial state, that's the little I there, sometimes not. I'm not going to worry about it too much. So we will say an equivalence relation R on a set S is a bisimulation if whenever you take a related pair and then you look at R closed. So an R closed set simply says if a point is in the set, then anything related to it by R is also in the set. If R is an equivalence relation, then this simply means some union of equivalence classes. So if you take an R closed measurable set, that was practically the only thing we had to do, then you want the transition probabilities of S to that set and S prime to that set to match up. Okay, so you can't talk about point-to-point transition probabilities, especially not in the case where your underlying system might be continuous. So we have to talk about transition probabilities to measurable sets. And also because probabilistic bisimulation is not just concerned with matching the transitions, but also with the transition probabilities, you have to essentially think of them as unions of equivalence classes. I go to sets that are already matched up. Okay, so that's the definition of probabilistic bisimulation. And we'll say two states are bisimilar if they are related by some bisimulation relation. Okay, so that's, again, secretly you can see that as a greatest fixed point definition of some kind.
Is it obvious that in this context the union of two bisimulations is a bisimulation?
It's not obvious, but it's easy.
Okay, because before it was obvious for the standard definition.
Right. So as I said, it's not obvious, it's easy. Easy means...
True.
Yeah, well, usually easy things are true. So yes, easy means I'm not going to show you the proof, but I'll show it to you next week if you ask me again. Okay, now we come to the heart of the matter. A logical characterization theorem for these things. So I should say, for the discrete case, people studied discrete probabilistic transition systems before, and they studied a number of equivalence relations, testing similarity and bisimulation. So I should be saying strong probabilistic bisimulation all the time, but let me drop all those adjectives. And what they showed was that there was a logical characterization of bisimulation. However, they had the following kinds of restrictions on the systems. So first of all, it had to be finitely branching. But in fact, stronger than that, there had to be given in advance a bound on the degree of branching. So it's not just finitely branching, but some number had to be specified, like 17, and then we're not allowed branching more than that. more stringent still was a requirement that all the probabilities that appeared in the description of the system had to be integer multiples of some small number. So it had to be some fixed small number epsilon, and everything had to be some multiple of that given small positive number. I'm not sure why I'm saying small. It didn't have to be that small, but you know what I mean. Some smallest probability that was the only thing that was allowed to appear. So there was a very discrete character to the whole thing. The logic itself had negation in it. Or there were other variants that didn't have full-blown negation, but all of them had some kind of negative construct. For example, a formula that said, this system cannot do an A action at this stage. Okay, so you will notice this logic, which I still haven't explained, has just the atom true, binary conjunction, and this modal operator, which I will explain in a minute. Intuitively, it means a system or a state that satisfies this formula can do with probability strictly greater than q. It can do an A transition and wind up in a state that satisfies phi. Okay, so it's a standard one-step modality that you would expect for this kind of transition system. Nothing negative. So it's a purely, so you notice the must, which is the dual to the may operator, is not there. So that has a hidden negation in it. Nothing like I cannot do an A is there at all. So this was a purely positive logic. Another famous Joseism, the first time she presented this result, people absolutely didn't believe it, and they jumped up and said, no, this can't be right. And again, not being entirely fluent in English and not knowing how to be super polite, she said, be quiet. At the end of my talk, you will have no more doubts. So, people were so shocked by this, they just stopped asking questions. So, yeah, so these were the surprises. So, remember I said that for the discrete case, you had this strong finite branching assumption. This is the continuous case. Finite branching assumptions would be completely silly to impose in such a situation. You're thinking perhaps of something diffusing across the real line. It's not even going to be countably branching. It could well be some kind of uncountable branching. This is why in the beginning we were not that optimistic that there would even be a logical characterization, because we were thinking we might have some kind of ridiculous infinitary conjunction. But magically all these things turned out to be unnecessary. And it wasn't, the proof doesn't go by the usual combinatorial arguments, which are extremely clever in the existing work. Instead, it used some rather unexpected machinery about analytic spaces. So let me give a formal definition to this. I've told you the intuition. We'll say a state satisfies that if with probability strictly more than q. By the way, it doesn't matter that much if you change it to greater than or equal to. You can prove the same theorem. It's just easier in the one talk to stick to one consistent interpretation. So strictly greater than q with probability strictly greater than q, I can do an A action and wind up in a state that satisfies phi. So A is an action, q is a rational number between 0 and 1. Why rational? So that I'm defining only countably many formulas by this syntax. Okay? And formally, I have to define it by this hodgepodge of Greek symbols. So you might say, why didn't you just define what it means for this, to have the set of states that satisfy phi, and then say the transition probability into that is greater than q? It's because these transition probabilities are only defined on measurable sets. I don't a priori know that the set of states satisfying phi is a measurable set, so I have to say it in this awkward way and then immediately prove a lemma saying that those sets are measurable. Okay, which is a very easy lemma, and I'm going to skip it. So our basic result appeared in Lix, and then with the usual delay, it appeared in a journal. Okay, so why can't this possibly be correct? Well, let's look at the non-deterministic case. So here there are no probabilities. It's a completely finitary indeterminate situation. And so we have these two systems that we're comparing, S0 and T0. You see, S0 can have a branching coming out of it under an A action. T0 does not. And so it's an easy exercise to show that if you write down a basic modal formula, there is no way you can distinguish these two without using negation. You can easily prove that by induction on the structure of positive formulas. By easily, I mean I've even put it on midterm exams and my students have been able to do it. So it's a really easy proof, and this is why people immediately said our result can't possibly be right, because this is you can't do this without negation. There's a simple negated formula that distinguishes them. Basically, you have to be able to say, I can do an A action and go to somewhere where B is impossible, which is not satisfied there. But to say a B is impossible requires some kind of negative construct. Now, if you add probabilities to the transitions, so let's say this now happens with a probability P, and that happens with probability Q. This one happens with probability R. Remember, I said sub-probability, so this doesn't have to be 1, nor does the sum of P plus Q have to be 1. Could be something less than 1. And these unlabeled ones, I just mean probability 1 in that case. So if it so happens that the sum P plus Q is different from R, either strictly less or strictly greater, well, then there's always a rational number in between them, and you can write a formula that will readily distinguish them because they'll have different probabilities for responding to an A. Okay, suppose P and Q exactly equals R, and suppose P is strictly greater than 0. Now, if P is in fact 0, then of course this is the same as that, and they should indeed be bisimilar. So if you're really saying they're not bisimilar, it's because P plus Q, because P is strictly greater than 0. So if P plus Q is exactly equal to R and P is strictly greater than 0, then Q is strictly less than R. And so now I can use some formula, I can find some rational number in between Q and R and distinguish them by seeing how they respond to a B. Okay, so I have constructed positive formulas in this case by exploiting the probabilities. Of course, this is not a proof. Sadly, you cannot prove things by killing the first counterexample. So, but it suggests that something more tricky is happening than you might otherwise think. Okay, so now let me begin the proof of the logical characterization. So first of all, this bisimulation is a very strong relation, and not surprisingly, it implies logical equivalence. It's an easy proof by structural induction on the formulas, and if you want to see it, you should look at it some other time. It's very easy, and it'll be on these slides. Okay, for the reverse direction, we were stuck for a long time. And we had this idea that perhaps things would be better behaved if we worked on Polish spaces, right? Now, to remind you, a topological space is called separable if it has a countable dense subset. And in the case of separable metric spaces, this is the same thing as saying that it has a countable base of open sets. Now, a Polish space is the topological space underlying a complete separable metric space. Of course, you cannot just say a topological space is complete. That doesn't mean anything. But it has a metric. Then you can talk about it being complete. But the point is, we don't actually care about the metric. We care about the underlying topology. So that's a Polish space. And measure theory works well on Polish spaces. Okay, so still you might think, why did topology creep into this story? So as I said, I think I said this before, measure theory works really nicely on Polish spaces. For example, if you just look at this obvious thing, you take the Borel sets of x1 cross x2 in the product sigma algebra, and you take the product sigma algebra of the Borel sets of x1 and x2. They might or might not be the same, in fact, in general measure spaces, but they'll always coincide with Polish spaces. I should also mention in passing, the monad I defined yesterday can be defined on Polish spaces. So this was not something in Lauvier's original notes, but this was worked out carefully by Jiri herself. Analytic spaces, where did these things come from? So, well, there's this famous book by, is it Lebesgue? Yes, I think it was Lebesgue, who wrote this famous book on measure theory, on measure and integration. And he made this remark that if you take a Borel subset of the plane R2 and project it onto the x-axis, then clearly the projection is Borel. Right. So a young student in Russia, Suslin, was reading this book and he said, gosh, I must be stupid. I don't see why this is true. And he struggled with it for a long time. And then he took it to his advisor, Luzin, and they struggled with it all day and they couldn't do it either. And then Suslin went home and invented analytic sets, which are a counterexample to that claim. So analytic sets are basically things that you get by looking at images of Polish spaces under Borel functions. So in fact, there are 6 equivalent definitions. Maybe I will actually draw things on the board. So you can take 2 Polish spaces, x and y. You can look at a continuous function f, and you can look at the image of f of x, the image of x under f in y. That set will be analytic. So you can take that as the definition. But then you can also notice that if I change f from being continuous to being measurable, you don't actually enlarge the class of analytic spaces. So this is a bit of a shock, but it is true. It doesn't matter whether I say f is continuous or f is analytic. Okay? It doesn't matter if I say I take x or if I take a Borel subset of x. So if I look at the continuous or measurable image of a Borel subset of x, I get the same class of analytic spaces. So I've just given you 4 definitions of analyticity. And then it doesn't matter if I take a generic Polish space or a very special one, namely n infinity. So the important point about analytic spaces is that they are nice and stable under things you want to do to them. And one of the things you want to do to them, especially as you see, soon I will be constructing equivalence relations to talk about bisimulation, is I want to quotient my space with an equivalence relation. And Polish spaces are not so nice. So partly, as I said, this whole thing took a long time before we got off the ground. And one of the things that stymied me was I couldn't prove that if I took a Polish space and took a quotient of it, that I would get a Polish space. And the reason I couldn't prove it is because it's false. And Mike Mislov pointed this out to me. So you take, for example, the positive quadrant of the plane. And rather than showing you an equivalence relation, I'll show you equivalence classes. So you take the hyperbolas. And you try to define a metric on these hyperbolas. You see they all scrunch together. It won't, in fact, be a metric space or metrizable. So we needed something else. So I didn't know, I had never heard of analytic spaces at this point. And I was staying at the university at Aarhus, which is a wonderful place. Kusha and I spent a year there together once. And so I was visiting again one year. And there's a little flat on the top floor of the computer science building where you can stay. And the key to that apartment also opens the library. And also opens everyone else's office. So that is one of the charming socialist aspects of life in Denmark. So everyone's key opened everyone's office. And also my apartment. So so one night I was sleepless, being jet lagged, and I went down to the library and I started browsing through various books. Some years before that, I remember Professor Scott told me I should look at descriptive set theory because it'll bound to be playing an important role in what I was doing. And of course, it didn't immediately, I didn't do this immediately, but I tried. I looked at a few descriptive set theory books, but I couldn't see the connection right off the bat. But then miraculously, as I was browsing randomly in the library, I found some lemmas about analytic spaces, which of course is kind of one of the starting points of descriptive set theory. And it turned out to be the key that unlocked some things. So analytic sets do not form a sigma algebra, but they are in the completion of the Borel algebra under any probability measure. So there's what are called universally measurable. And you can do lots of nice things with them. Importantly, disintegrations, namely regular conditional probabilities, can be defined on these analytic spaces, not just on Polish spaces. And here are the 2 amazing facts that completely destroyed my night's sleep. Supposing I have an analytic space and an equivalence relation such that there is a countable family of real valued measurable functions from the set, oh my God, why did I call this S? From A to R, such that 2 points are equivalent if and only if all the functions agree on them. Okay? So an equivalence relation might or might not have this property. If I have this property, it's called a smooth equivalence relation. So if I take an analytic space and a smooth equivalence relation and I quotient it by this, and by quotient it I mean set theoretically the obvious thing, I take the equivalence classes, but I look for the finest sigma algebra making the canonical surjection measurable, then that thing is also analytic. Okay, so this is one somewhat amazing fact, maybe not so amazing because analytic spaces have these strong stability properties as we've already seen. But it gave me hope because this was what I had been trying to do. I said, maybe we should be doing analytic spaces. Now, here's the thing that I'd never dreamed of. If you take an analytic space and with its Borel algebra sigma, and suppose you have a sub-sigma algebra of it, okay, sub-sigma algebra of it, which separates points. So that means if I have any two distinct points, I promise you I can find disjoint measurable sets in my sub-sigma algebra that contain these 2 points. Okay, so that's what it means to separate points. And so that means it's not too fine. I've not made it so crude that it can't even tell the distinction between points. But it's not too huge. That means it's countably generated. Then this sub-sigma algebra is actually the whole thing. Okay, so this is called the unique structure theorem. There is no room to put a countably generated sigma algebra inside that's a strict sub-sigma algebra unless you want to make it so crude that it doesn't even distinguish points. Okay? Why is this relevant? You will see presently. Okay, so keep these facts about analytic spaces in mind, and we will now go back to try and prove the main theorem. Okay, so here's the idea. Basically, we want to show that the equivalence relation S and S prime satisfy the same formulas of the logic. That's an equivalence relation, of course. We want to show that that is a bisimulation relation. That will, of course, prove that that logic characterizes bisimulation, because it will tell you if two things are logically equivalent, they are in fact bisimilar. Now, we can easily show that if I take sets of this form, so this brackets, I'm assuming everybody implicitly understands it. This is simply the set of states satisfying a formula. So if I look only at sets that are the denotations of formulas, then it's easy to show that, right? Because if that weren't true, then I could write down a formula on which they disagree, because there would be some difference in the transition probabilities, and I'd put a diamond AQ in front of my phi, and I'd get formulas on which they disagree. Okay, but of course, these are far from being all the sets. Now, essentially, we use the lambda pi theorem to show that we can get a well-defined measure on the sigma algebra generated by such sets, such that the above equality holds. So of course, these sets don't form a sigma algebra, but they generate one. And then we use these special properties of analytic spaces to show that this actually is everything we want. And that's the outline of the proof. Okay, so how do we proceed in detail? So we have to, the first thing we're going to do is we're going to take our original space and quotient it by this logical equivalence. Okay, so we've got an LMP, so defined on an analytic space. We have the equivalence relation, which says that they obey exactly the same formulas of our modal logic. Two states are logically equivalent if they obey exactly the same formulas. And now I claim that's a smooth equivalence relation. Why? Because the indicator functions of the definable sets are exactly the things that characterize that equivalence relation. Okay, so recall this notation. So this means the set of states that satisfy the formula phi. This indicator function says, if you're in that set, I'll give you 1, otherwise I'll give you 0. And two things agree on all formulas precisely when all these functions agree. So these are just the characteristic functions of the sets defined by the formulas. So here we have a countable family of measurable functions. How do I know they're measurable? Because these sets are measurable, such that two states are equivalent if and only if the functions agree on all of S. So there we have it, a smooth equivalence relation. One of the reasons why I restricted the logic to have only rational numbers in the logic. The systems, of course, can have arbitrary real numbers, but not the logic. So I get a smooth equivalence relation, I can quotient it, and I know that the quotient space is analytic, and I know that the projection map is measurable. That's almost everything I need, in fact. Okay, so far I know that this quotient space with its quotient sigma algebra is an analytic space. I now want to endow it with with a transition probability function. Okay. So there is a kind of functional analog of this notion of bisimulation called a zigzag, which is another term we picked up from modal logic. So if I have two of these systems, I'm suppressing the sigma algebra. Then a zigzag is a function such that oops, too many parens. Okay, so basically this is saying this F preserves transition probabilities. All right, so I'd like to say, I'd like to be able to put a transition probability structure on top of this space in such a way that the projection map, the canonical surjection from the set onto its quotient, is in fact not just measurable, but actually preserving the transition probability structure, a so-called zigzag. All right, so that's easy. I'll just define this to say, if you give me a point T down here in Q and a measurable set there, I will look at the inverse image, which I know is measurable upstairs because Q is measurable, and I look at S, where S is some chosen point in the inverse image of T. So we need to check that this thing is well defined, because I could have picked any old thing I want. How do I know that the transition probabilities I get down there are actually well defined in this way? So the first thing to note is this curious fact that Q inverse of Q of the denotation of a formula phi is in fact exactly the denotation of phi. Okay, and here is in font too small for you to read a demonstration of that fact. It's a totally elementary thing. That's why I don't want you to read it. But if you're truly suspicious, you can check it out. Anyway, the point is, normally the forward image of a set is absolutely not measurable. And that's not the definition of a measurable function, right? Its inverse images of measurable sets are measurable. But this time, it so happens that the forward images of these sets are, in fact, measurable sets downstairs, precisely because of that. Okay, so thus, these sets are measurable. Okay, so I can look at the sigma algebra generated by these sets. So, and I'll call this lambda, let's say. So it's a sub-sigma algebra of omega. Now, this is countably generated, and it clearly separates points, right? Because if you land on different points, then there's some formula on which you disagree. So by the unique structure theorem, it is all of omega. So this is the power of this theorem. You start thinking, oh, I can only do this on the definable sets, and that surely must be far too few of them. But this theorem tells you, don't worry, just do it on what you know how to do, and I will take care of it for you. So the unique structure theorem really helps us there, because now we know that this fact doesn't just generate some sub-sigma algebra, it generates all of it. Okay, it's still, so rho is defined on all the sets. I still don't know that it's well defined, however, because I could have picked different points in the inverse image of, of my point T, and how do I know they match up? So you remember on Tuesday I told you why I loved pi systems. It's because if you have a pi system generating a sigma algebra, and you have two measures that you know are measures, and you find out that they agree on the pi system, they agree on the whole generated sigma algebra. Now this collection of sets, the generating sets that come out of the logic, form a pi system for the simple reason that they contain conjunction. That's why conjunction is in the logic. So everything that's in the logic has to be there, more or less. Okay, so if we show that the two measures that you get by choosing different points actually agree on these sets, they will agree on all of omega. Okay, so supposing I have Q of S and Q of S prime, both of them going down to T, then it so happens that T of S phi has to be equal to T of S prime phi, and this is a simple interpolation argument, right? Because if these things are different, then they will disagree on some formula. I will always find some rational number between those two transition probabilities. I can use that to annotate my diamond, and as they say in Australia, Bob's your uncle. Never understood what that meant, but there it is. Okay, now look at this. So I now want to show that the transition probabilities I get upstairs have to be the same. So if I look at T of S, Q inverse Q phi, these must match up because these things are in fact those. I proved that. Okay, so that is what tells you that rho is well defined. All right, and we have the zigzag property that we were looking for, and we now know that this rho is actually defined everywhere, not just on the definable sets. So that's it. We just have to complete the argument by looking at what happens to these equivalence closed subsets of S. That means unions of equivalence classes. Okay, so let X be any such set, and you look at Q inverse Qx, so that's equal to X, and we know that Qx itself is an element of omega. So if we compare these transition probabilities, TASX, this is just a simple inequality, simple equality I proved before. This is the zigzag property that gets me down there. Well, Q of S and Q of S prime are the same thing. They're logically equivalent, so they go to the same equivalence class. So then I go back up, and I get that, and therefore this is just X. So I get the equality that I want. Okay, so for any equivalence closed sets, bingo, the transition probabilities match up. Okay, so this is a bit like, you know, when those tourists climb up Mount Everest and they have Sherpa guides who kind of drag them up there. So perhaps you feel a bit like that some black magic happened. And indeed, it does look a bit like black magic, because suddenly, instead of what you might have thought would be some combinatorial argument about the structure of the transition trees, got replaced by some measure theory arguments. I think a more combinatorial argument can be given, certainly not by me, but Bartek Klin has given a cleaned up proof of this. Maybe one day we can persuade him to give a formal or informal talk about it, but still uses some measure theory ingredients, at least the lambda pi theorem. Okay, so that's bisimulation. What about simulation?
Prakash, before when you went to the logic, you had not put any negation, right?
Right.
But you saw that you can somehow simulate negation, right? I mean,
No, I never said that.
Okay. You bypass the...
Yeah, can bypass it is very different from simulating it.
So this logic is the maximal in some sense. You can't put more features in the logic and still get the same result, or you could?
No, you can't put fewer features. It's the minimal. You can't take any features out of it and still get the same result. You definitely need conjunction. You definitely need that modal operator, otherwise you'll not be able to say anything about transitions, and that's all you've got.
But you could put other...
Oh, so on the other side, you can put lots of stuff.
Things that preserved by simulation.
Yes, so very, very rich logics preserved by simulation. The point is to characterize it, all you need is this extremely simple logic. So that should be, yeah.
So your setup presumably generalizes standard probabilistic by simulation on finite state transition systems, right?
Yeah.
So suppose, and we know how to compute probabilistic by simulation on finite state transition systems easily. Suppose I do that and I find the two states are not bisimilar. How can I efficiently generate a formula in your logic?
Yeah.
How big would that be? So is it a small thing? Is it just sort of something that? So
I know I should be giving you a really quantitative answer, and I can't remember, but it is reasonable. Yeah. So Jose's thesis has an algorithm for generating the formula.
Okay.
Yeah. It's a good question, and I should know this, but I still don't remember. But it's not hard. It's neither difficult, the algorithm, nor is the formula generated big.
Okay. In a sense, what this is saying is that you can simulate negations.
No, it depends.
That distinguishes, you can write it with negations probably.
What?
You can probably write it with negations, the one that distinguishes, but by the standard argument or something.
But he's saying he doesn't have negation.
Yeah, but then there is an algorithm that transforms it into a monotone one. So they have an algorithm that.
So our algorithm.
States that are not similar or bisimilar. But you don't have the formula that distinguishes them.
Yeah.
It generates the formula, and it generates the formula in this logic. No doubt, if you made richer logics, you would get much more compact formulas. Absolutely.
Yeah. No, I was talking about the positive formulas.
Yes. So you can generate an algorithm for it. By the way, you also, I thought you were going to ask something else, which was that, so as I said, at the time that we did this proof for the continuous case, the people who had done the discrete thing still had negative stuff. So this was also, after the fact, a proof that for the discrete world you didn't need it either. And I still don't know a pure combinatorial proof of logical characterization for discrete systems that doesn't go through some amount of measure theory. So that's interesting. You have one?
Yeah, I would.
Oh, awesome. Next week.
But I have another question.
Yes.
So this proof really crucially depends on the set of formulas being countable.
Yes.
Which means that you rely on the set of labels being countable.
Yes.
So the question is, how do you sleep at night? Because it shouldn't matter. Because both in logic and in by simulation, we universally quantify over the set of labels, and it's really independent what happens between different labels.
Mm-hmm.
We should be fine with uncountably many labels. There's something wrong here, morally.
Morally. It's true that if I was trying to describe systems like steering a car, I would like to have uncountably many labels. I mean, right? Because there's a continuum of possible ways of taking actions, namely.
For example, if you think about label transition systems,
mm-hmm.
then for the logic with binary conjunction to characterize by simulation, you need finite branching. But the set of labels can be anything. You don't need any assumption on that. But here suddenly you impose this assumption, which is very strange. Looks crude. I do the same, but it somehow feels wrong.
Let's solve it during the semester. It's a good point. I mean, I've often responded to this by saying, well, I can make countable approximations to continuous label spaces, and prove things there. But you're right. Maybe we should try to do it for uncountable label spaces. Certainly my friends in robotics always say, what about uncountable labels? Because those are the people who are indeed steering things using continuous parameter spaces to guide their robot. Of course, some people drive as if they were discrete, but mostly we would like continuous label spaces. I totally agree.
Just so I understood, so what needs to be countable? The number of distinct formulas of...
Yes.
But I thought the formulas have also parameters which are probabilities in them.
Rational.
Oh, you just have to, okay, so for that reason alone, you have to restrict them to be rationals. I see.
Rationals are good enough because, fortunately, between any two reals, there's a rational. And So that is what allowed me to construct distinguishing formulas, even though the transition systems themselves were not restricted in that way.
Right.
Yeah. Okay, so let's talk about simulation. So I won't prove anything here. So simulation is just like bisimulation. You see that I've replaced this, what had been an equality before, by an inequality. So basically, it says that S prime can do everything S can do with better probability. And now you can ask, well, is there a logical characterization for simulation? Now notice if the logic had negation, you would have no hope of this, right? So it's important that the logic was purely positive, so it was even a viable question. Of course, it doesn't mean that the answer is yes. It just means it is a question that can be asked. So you can show this, that if S simulates S prime, then S will satisfy all the formulas that S prime satisfies, possibly more. Okay, so that's nice. But what about the converse? So it turns out, so I was sure that this was true, but Jose came up with a counterexample. So here is her counterexample, and maybe how much time have I got? Yes, I think it's worth drawing this so that when I flip to the next slide, you will still see this. Here is S. It has two transitions. So when I don't put a label, it means the label is A. And when I don't put a number, it means the number is 1. So this is just to prevent it from being too cluttered. Here is T. Maybe I'll put T on this side. So T has 4 things coming out, each with equal probability. And then I'm not going to name all the states. And this one is a dead state. Okay. So all the transitions coming out of S or T are labeled with A. So this is 4-way branching with uniform probabilities, and this state is called T1. I didn't bother to name the dead states or these ones. Now, you can give an example of a formula that is satisfied by T, but not by S. Okay? Because T has the possibility of going somewhere and then having both A and B available to it. That doesn't happen there. Okay, if you wind up here, you can only do A. If you wind up here, you can only do B. So clearly, these are not bisimilar. However, it's not true that T simulates S, because there's a formula with disjunction that's satisfied by S, but not by T. So disjunction, if you recall, was not in my logic before. But if I consider logics with disjunction, then this particular formula is satisfied by S, but not by T. Because this says, with probability greater than 3/4, I can either do an A or a B. And that's exactly, this is with probability 1. I can wind up somewhere where either I can do an A or I can do a B. Whereas here it's exactly 3/4. Remember my annotations were, it had to be strictly greater than. All right, so this leads you to suspect, in fact, even though it looks as if T should be able to simulate S, it actually can't. So how do you give a logical characterization of simulation? It turns out that you have to add disjunction, finitary disjunction to the logic. Still, of course, everything is positive. And this proof turned out to be quite a bit harder, but maybe Bartek will come up with a simple version in a few weeks. But with this logic, we were able to prove that S1 simulates S2 if and only if, for every formula of our logic with this junction, S1 satisfies phi implies S2 satisfies phi. And the only proof that we know uses domain theory. So one can actually organize LMPs into a domain and look at Samson-Abramsky's work on logical characterization of simulation, on domain theory in logical form, and apply it, and then ultimately we were able to prove this result. You can go back to sleep, Samson.
Without Pauli spaces and all that? Or? I'm confused. Before you had all this machinery from descriptive set theory.
No, we still have that machinery.
And
domain theory. That's really fun, yes. Okay, so as I remarked before, other logics can also characterize by simulation. For example, if we add negation, it's still fine. And by the way, several people have suggested that somehow I'm using arithmetic on the probabilities to simulate negation. It's absolutely not true. Because if I had a logic with finitely many actions, super crude, Bartek, finitely many actions, and I had negation in my logic, I could write down a formula that's only obeyed by the dead process, which basically says, no, I can't do an A, no, I can't do a B, no, I can't do a C. And nothing in my logic allows me to write down a single formula that's only satisfied by the dead process. This shows that it's not that I'm somehow able to simulate negation, it's just that I'm able to avoid it. And of course, much richer logics are also invariant under bisimulation. So in particular, fixed point logics and all kinds of things that you would actually want in an expressive logic for reasoning about probabilities, for reasoning about probabilistic systems. So let me wrap up. Strong probabilistic bisimulation is characterized by a very simple modal logic with no negative constructs. There is indeed also a logical characterization of simulation. There is a metric on LMPs which is based on this logic. So just to anticipate some of the same propaganda that I will be spouting tomorrow. Okay, so it's fine to have a theorem like this, but is it really sensible to work with this kind of concept when you're dealing with probabilistic systems? The definition of bisimulation said probabilities had to match exactly. So we're requiring exact real arithmetic somehow, or exact comparison of real numbers, and it really doesn't make sense. If one had two bisimilar systems and then you perturb the probabilities just a little bit, suddenly you would say, they're not bisimilar anymore. This is too drastic a response. Rather, one should have some kind of metrical notion that measures closeness so that one can gracefully say, the things are getting less and less similar, and there's some numerical measure of how far apart they are. So this metric is what I will be talking about tomorrow, a metric that measures closeness of behavior rather than exact equality. But that metric is based on ideas that come out of this logic. There are things that I didn't really understand. Why does proof require so many subtle properties of analytic spaces? It's true that Bartek has gotten rid of many of them, but I think it's still true that it's not purely combinatorial. It's kind of a measure theoretic argument. It turns out, though, there is another definition of bisimulation. You see, the thing that we did here was focus on points, and on points being bisimilar. And maybe one shouldn't even be talking about points. One should be talking rather about events. So there was another definition of bisimulation we gave much later called event bisimulation, which is much more adapted to the idea of working with measurable sets rather than these very sharp, pointy things. And it turns out that the proof of logical characterization is easy and works for arbitrary measurable spaces, not just analytic ones. But then, of course, if you go back to the people who like the traditional notion of bisimulation and they ask, well, when do they coincide? They coincide on analytic spaces. And then, so you can say, well, instead of saying you have a hard proof of the logical characterization of bisimulation, you can say we have a hard proof that these two different notions are the same. And I don't have any slide 30 out of 29 today, so I will end there. Thanks. So before people run away, I should remind you we're supposed to, Kusha? We're supposed to be lined up for a photograph of the boot camp right after this. But any quick questions before we go for the photo? No? Okay, good.